Good evening. This is the third, I believe, in the sequence of Qulsar videos, and my wife tells me I should not give up my day job. I'm not a good actor, but we are talking about time error. Let me refresh your memory a little bit about time error. The notion of time error is that we are comparing two clocks, and we think of two clocks. In our mind, we think of clock waveforms, typically square waves, and if you have one clock relative to the other clock, and you try lining up the edges at some point in time, this time difference between the edges is what we refer to as a time error. Now, clearly every clock has a periodicity associated with it, so you have some basic T sub 0 is the time unit between measurements of time error. So we have a very natural discrete time sequence, which I'll refer to as x of n T sub 0, where each of these measurements is x. So this is x of n, the next one would be x of n plus 1, etc. When we think about this time error, it's convenient in shorthand notation to refer to it as x of t. And I'll just talk about some of the aspects of this time error which are of interest. This time error is going to have a component we call a sub 0, some constant value. You're going to have some deterministic components which are related to, I'm going to put one first, y of times t, where y is a fractional frequency offset. So that's the frequency difference between the two clocks. You can have a drift component. So we think of the first clock as the reference, the second clock as the clock under which we are measuring. It can have a constant error, a time offset which is linear in time corresponding to a frequency offset, a drift term, and then there's always a catch-all random noise. So when we talk about clocks, and especially locked clocks, when you take one clock and lock another clock to it, this is the kind of equation we have in the back of our mind regarding error. Now let me tell you what I mean by locked clock. Suppose you have the clock number 1, it is generating some kind of a signal, and that is being transmitted somehow to the other end where you have the second clock, clock 1, clock 2, and we are supposed to lock clock 2 to clock 1. When we lock these two, we want these two, number 1, to be equal in frequency, so this goes. So we have to make sure that whatever we transmit from clock 1 to clock 2 does not introduce any frequency offset. Secondly, we want the second deterministic part to be 0. So whatever means we use to transmit timing information from 1 to 2, we want d to be equal to 0. When we are dealing with frequency, a sub 0 being a constant does not play very much of a role. So when you think of transferring from clock 1 to clock 2, the timing information, it's just a noise. So the clock 2 then, when it recovers clock, essentially, it is introducing a filter which will reduce essentially the random noise to a level which is appropriate. Because the next talk we'll talk about how we can kind of quantify this random noise and how well this locking is happening.